Hello, and welcome back to our introduction to the C programming language. This is our third session. A quick recap from last time. We went over the C preprocessor, compile time directives, use of typedef, and we had a brief look at how a C program looks and the various parts therein. This time we'll be going over the built-in data types to C, a few qualifiers to them, constants and strings, storage classes, how scopes work in C, and how they hide data from each other, and data initialization. So, built-in data types. C has a handful of data types, each with a keyword associated with them. There are technically more than this, but these are the easiest ones. There's the int, which is short for integer. There's whole number. They are whole numbers with a valid range minus 32767 through 32767. In memory, they take up 4 bytes. They are signed integers by default, which means they can be negative, but there is a qualifier called unsigned that you can stick before an int, so you declare an unsigned int. That will make it so that it can only hold 0 and positive numbers. That all takes up the same amount of memory. There is the char, or the car, you might hear it pronounced. I tend to swap between the two. These are individual ASCII characters. In memory, they take up 1 byte, and if you need a character literal, you enclose it in apostrophes. Like in these examples here. You have a capital A, a C, a 3, and an asterisk, all of which just enclosed by apostrophes. The C compiler will interpret those as character literals. There is the float and the double. These two are very closely related. They represent real numbers. By that, they have an integral and a fractional part. You can look under the hood at how these are represented elsewhere. It is beyond the scope of this class, but it is useful information to know. They can be represented using decimal or scientific notation. You can use different ways to format output from the computer to get them in different ways. And the float takes up 4 bytes of memory, and the double takes up 8 bytes. This 8 bytes allows it to be double the precision, hence the name. Constants. You heard me mention unsigned earlier. There are other qualifiers to data types. For example, there's const. In C, there are 2 ways to define constants. You can use the preprocessor, like we went over last time, or you can use the const keyword. The preprocessor works how we described last time. You define a constant, and the preprocessor does a find and replace. Every time it, for example, sees the word length, it's going to replace it with the number 10 before it hands this off to the compiler. So here we would get length, replace it with 10. We see width, it just gets cut out and replaced it with 5. We get new line, it's cut out and replaced it with this new line character here. This is what's called an escape character. That / and a 1 or 2 characters after it denotes a character that cannot be typed normally on your keyboard, but is still important to be able to use for output formatting or for a handful of other things. On the other side of the coin, we have the const keyword. Consts can be of any type, but the key difference here is that the const variables are, well, variables. They have a specific location in memory. So this length here takes up 4 bytes in memory somewhere. What this means is that with some shenanigans, you can actually ignore the const keyword, meaning const acts more as a reminder to the programmer than as something the compiler and runtime will enforce. In general, it's a bad idea to do that, but it is technically possible. Besides those minor semantic differences, these 2 programs here, they both do the same thing. So, strings. we've seen characters. Strings are, under the hood, just arrays of characters. We'll go into arrays in more depth a couple of lessons from now. Suffice to say that an array is a collection of the same kind of data, just multiple of them. In C, and in anything that uses the C style of string, strings are terminated with a null character. That is to say, when considering a string, the compiler will run through that string until it finds a null character that's /0 or just a byte of all zeros, and at that point it will consider the string to have ended. We have a couple of examples here of two ways to get a string. So we have char greeting. It's an array of 6 characters, and it is defined using these curly braces as capital H, E, L, L, O, and the null character. A more concise and more human readable way to do it is to just char greeting is an array that is as big as it takes to hold the string hello. You can make string literals by surrounding them with double quotes, and when you do that, the null character at the end is implied, meaning that you don't have to specifically state it. You get a quick diagram of what this looks like in memory here. Another sneak peek, arrays in C start at an index of 0 and end at an index of their length -1. And you can see by the addresses here that the array is contiguous in memory, meaning it's all one chunk with everything right next to each other. The C standard library, which the string library you can include by using include string.h, has a handful of operations that you can use for parsing and manipulating strings. Strcopy will copy the second string into the first string, assuming there is space. If there is not space, strcopy will not say it failed, it is just liable that your program will crash because it looked at memory it's not supposed to. Strcat will do a similar thing. It will take S2 and just tack it onto the end of string 1. So again, make sure that your arrays have the space to do that if that's what you need to do. Strlen will return the length of the string, not including the null character. The null character is always implied and never counted. So in this case, we would have strlen run across the length. We'd get 1, 2, 3, 4, 5. There's the null character. Our result is 5. Strcomp will compare string 1 and string 2. Technically speaking, it will determine if string 1 is lexicographically less or greater than string 2. The specifics of that are really not necessary to know. Just know that it returns 0 if the strings are the same. It will return something less than 0 if S1 is less than S2, or greater than 0 if S1 is greater than S2. For the most part, you care if it is 0 or if it is not 0. Strcr will look through a string and return a pointer to that string of the first occurrence of the character ch in string S1. As a quick example, let's say we pass this hello as S1 and the letter L as ch. Strcr will go through the string, say this isn't an L, this isn't an L, this is an L. I'm going to return a pointer to this character, which is basically an index into this array. So specifically, it'll return this address here. Strster will do a very similar thing. It will look for a substring S2 in a longer string S1. If it finds one, it will return a pointer to it. If it doesn't find one, it will return null, if I recall correctly. So again, as a quick example, we pass this hello in as S1, and as S2, we pass in LLO. So we see This is not an L, so we move on. This is not an L, so we move on. This is an L. Next character in LLO is also an L. Okay, this is also an L, so we keep going. This is an O, and we have found the LLO. We're done. So we're going to bounce back here and return this pointer again. If that was a little complicated, we're going to go in depth into how pointers work in the next lesson. Storage classes. This is a useful trick. So a storage class determines how the C compiler and how the runtime manage the lifetime and storage of a variable. What that means is it determines how the memory is allocated and how long until the memory is reclaimed in the program. Like const and unsigned, they go before the type they modify. So what happens is you have the storage class, then any other qualifiers, and then the name of the data type. So the four types we have are auto, which is the default. It is implied whenever you declare a variable, like int amount over here. Technically, you can do auto int month, but I have never seen that done. Register, another one that's pretty rarely used, but it says that a variable should not be loaded into RAM. It should instead be held in a CPU register. In general, you're not going to need this because the compiler can optimize code better than you can. The compiler's job is dealing with the nitty-gritty of how variables should be stored, and it's just going to do a better job of that than any programmer can. Static. What static does is it instructs the compiler to keep a variable in existence during the entire life of the program. This can be done either in a variable scope or in the global scope. In the global scope, it is just always accessible, and its value is maintained however you change it. In general, it is mostly visible only to things that share a source code file with it. You can get around that using the extern keyword below, and we'll get to that in a moment, and there are examples in the next video. I know that I've been putting a lot of things off to that video, but trust me, I've written up some pretty useful examples that we'll go through line by line. Last one is extern. This is another signal to the compiler, but one that actually makes a difference this time. What extern says is, trust me, somewhere else in the code, in some other module, there exists either a function with a signature that looks like whatever I'm typing after, or there exists a variable with the name I'm giving you. Don't panic when I use this later in this file. Trust that the linker will find it. If the linker doesn't find it, then you've got problems, but the compiler will, in general, trust you when you use extern like this. So, scope and block structure. In C, scopes are defined by those curly braces that happen when you hold Shift and type one of the square brackets to the right of the P key. Scopes can be nested within each other, and they determine how variables can see and talk to each other. There are three places a variable can be declared in C. There is within a scope block, which is called a local variable. There is outside of all scopes, which is called the global scope. Be careful when declaring things in the global scope, or specifically variables. Functions have to be in the global scope. And in the definition of function parameters, that's between the parens, which are called the formal parameters of a function. The way scopes hide data from each other is that Lower scopes, meaning scopes that are nested deeper within those sets of curly braces, can see variables from higher scopes, but not the other way around. Or specifically, code in lower scopes can see variables in higher scopes. Let me see if I can find a way to explain this. If you have a variable in the global scope, and even though you can't have code in the global scope, let's pretend that you did for a moment. If you had code, executable code, in the global scope, then it would not be able to see any variables that are inside functions or inside lower scopes. Similarly, this is why a given function cannot see the variables inside any other function. We'll see why this is when we go into stack memory. Using global variables too liberally tends to result in sloppy programming with a lot of errors and a lot of data corruption. Use the global scope very judiciously if you, in fact, need to use it at all. Lastly, data initialization. This is different from declaration and assignment. In C, when you declare a variable, memory is reserved for that variable. But nothing else is done for that chunk of memory. The runtime just says, okay, you can have this chunk of memory and whatever's in it. Usually this means you'll be getting 0, but sometimes you can just get garbage. Modern compilers are pretty good at initializing to 0, but you don't want to rely on them for that. When you, in the same line as you declare a variable, you assign to it, like in the line down here, int I equals 0, this is called initialization. This tells the compiler, preserve this memory and load this value into that memory. This prevents you from getting any garbage data or any unexpected behavior. Again, initialization can only occur on the same line a variable is declared. If you don't initialize it, its value is undefined, and it's a good idea to initialize whenever you declare a variable, just in order to absolutely prevent as much undefined behavior as physically possible. One last note that's kind of unrelated. Assignment operators can be chained together. For example, this A equals B equals C equals D equals 10. Under the hood, this actually works from right to left. So what happens is this D equals 10 is resolved, then this C equals D is resolved, then B equals C, and then A equals B. And this would result in all 4 values being set to 10. Quick summary, we have gone over the basic data types of C, qualifiers, storage types, scopes, how scopes hide data from each other, and we have differentiated between declaration, assignment, and initialization. Next time around, we'll be going into the nitty-gritty of pointers, pointer arithmetic, dynamic storage, the size of operators, and pointers to pointers to pointers, oh my. I know pointer is a scary word for some of y'all. Don't worry, I will go as carefully as I can. As always, there are live coaching sessions from software design and engineering to C and C++ programming to whatever else you need, all on the website. Some extra resources if you decide you want to do some extra reading. And thank you for joining us.